In linear algebra, you basically study vectors and linear transformations. But in order to do that, you very often need to solve a system of linear equations. Right here you see an example of a system of linear equations. It's two equations in two variables, x and y. Now you probably already saw in high school how to solve such a system of linear equations. And maybe your teacher told you that a possible way to do this is, in this case, to add the first equation to the second equation. Now, why would you want to do that? You could do that to eliminate the variable y from the second equation. Because what happens if you add the first equation to the second equation? Well, x plus 2x becomes 3x, and minus y plus y becomes 0. On the right-hand side of the equation, you get minus 4 plus 1, so that's minus 3. Now let's say that the first equation just remains the same. Now you see that by adding the first equation to the second one, there's no longer a y in the second equation. So now we can simply read the solution for x from that second equation. And if 3x equals minus 3, then x must be equal to minus 1. Now what is y? Well, you can determine y by plugging in the value x is minus 1 in that first equation. What do you get? Well, 2 times minus 1 plus y equals 1. So minus 2 plus y equals 1, or y equals 1 plus 2 is 3. Here you see an example of a system with 3 equations and 3 unknown variables. Now, if you look at this, it's probably unclear how you can add equations to other equations in order to eliminate variables. So what we want to do is find an algorithm that we can use to solve a system of linear equations when you have any number of variables and any number of equations. Now, first of all, just to write things down in a more, simpler form, we're going to put this system of equations in an augmented matrix. Matrices are very important in linear algebra, and we'll study them more in depth in lectures that are still to come. But in this case, well, what is a matrix? It's simply a block of numbers. What are the numbers in this augmented matrix that is associated with this system of linear equations? Well, on the first row, it contains the coefficients of x, y, and z. So the first equation is x plus 2y plus z. So the coefficient of x is 1, the coefficient of y is 2, and the coefficient of z is also 1. Then on the final position, we get the number that's on the right-hand side of the equation, and that's 5. And then we do the same for the second equation and the third equation. As for the second equation, you get 2 times x, 3 times y, 5 times z equals 10. And for the third equation, you get minus x, so that's minus 1, minus 2y plus z equals minus 3. Now this thing is called the augmented matrix. And it's often convenient to put a vertical line right here to denote that that's the position of the equal signs. The book doesn't usually do this, but, well, it's convenient. Okay, now a little bit of terminology. This left-hand part is called the coefficient matrix because it contains the coefficients of x, y, and z. I already used the term row, and each of these horizontal parts of the matrix is called a row. As we have a first row, a second row, and a third row. The vertical parts are called the columns. So we have a first column, a second column, a third column, and a fourth column. Now what we want to do is replace this augmented matrix with another matrix that has the same solutions, but that is a lot simpler. And with a lot simpler, I mean, well, a matrix that contains a lot of zeros. Well, how can we do that? There are in fact 3 elementary row operations that you can perform on an augmented matrix that do not change the solutions of your system of equations. You can find these elementary row operations on page 22 of your book. Now, first of all, you can add a multiple of a row to another row. Second, you can swap 2 rows. And third, you can multiply a row with a certain non-zero number. So now let me try to use these elementary row operations in an efficient way to simplify this augmented matrix. And what I want to do is eliminate x and y from the third equation and eliminate x from the second equation. And then I'll show you that the system of linear equations that you obtain is a lot simpler and can be solved. Okay, so here you see the same augmented matrix, and this matrix still represents a certain system of linear equations. Okay, now I'm going to use these elementary row operations. The first thing I'm going to do is eliminate x from the third equation. Now what does that mean? I want this minus 1 to become a 0, because this minus 1 was the coefficient of x in the third equation, and if it becomes 0, well, then it says 0 times x, so we no longer have an x in the third equation. Now we have 3 row operations, and the one that we're going to use the most actually is adding a multiple of a row to another row. And in this case, we can simply add the first row to the third row. Okay, and I'll denote that like this: row 3 plus row 1. Now then we get a new matrix, and we will say that this matrix is equivalent. And we'll denote that with this little symbol. And equivalent simply means we get a new matrix, and we obtain that matrix by performing certain elementary row operations. So what is the matrix that we obtain if we add row 1 to row 3? Well, only the third row changes. So minus 1 plus 1 becomes 0. Minus 2 plus 2 well, also becomes 0. And 1 plus 1 becomes 2. And then finally, the fourth column, we get minus 3 plus 5, and that's also 2. Now everything else stays the same. So the first row remains as it was, and so does the second row. Okay, in the beginning I told you that I wanted to eliminate x and y from the third equation, and we got a little bit lucky because by eliminating x from the third equation we automatically eliminated y as well, because you see that we also have a 0 right here. Okay, now the final step in this case, in this example, will be to eliminate x from the second equation. So this 2 right here should become a 0. Okay, how can we do that? Well, we can take row 2 and add minus 2 times row 1. Or we can say, well, it's row 2 minus 2 times row 1. Maybe you already saw systems of linear equations in high school, and maybe you used a different type of notation for the elementary row operations. If you want to use your own notation, that's of course okay. So in this case, only the second row changes, everything else stays the same. So what happens to the second row? Well, the first element, the first number, there we get 2 minus 2 times 1, so that's 0. And that's, of course, exactly what we wanted. On the second place, we get 3 minus 2 times 2, so that's 3 minus 4, so that's minus 1. Then 5 minus 2 is 3. And finally, 10 minus 2 times 5 is 10 minus 10, and that's equals to 0. The first row and the third row, well, they do not change, so we get this matrix right here. Now, to see why this is actually convenient, what we just did, we can write this as a system of linear equations. As on the third row, we have 0, 0, 2, and then another 2. So this actually says 0 times x plus 0 times y plus 2 times z equals 2, or 2 times z equals 2. So that's the third row. On the second row, we have 0 minus 1, 3, 0. So this means 0 times x minus 1 times y plus 3 times z equals 0, or minus y plus 3 times z equals 0. And then finally, the first row is 1, 2, 1, 5. So this means 1 times x plus 2 times y plus z equals 5. Okay, so now I rewrote my augmented matrix in system of equations form. And actually now we can just read the solution of this system of equations. Because on the final line, the bottom line, you see 2 times z equals 2. So this means that z is equal to 1. On the second line, the second equation, there you see minus y plus 3 times z equals 0. Well, if z is 1, then this says minus y plus 3 is 0, or y must be equal to 3. And then finally, if we want to determine x, we can plug in y and z in the first equation, and then we get x plus 2 times 3, so 6, plus z, so 1, equals 5. So then we get x plus 7 equals 5, so x is minus 2. And this is then the solution of our system of linear equations.